does.
All right, so now that we've fixed the internet, let's try something a little easier, quantum computing.
Super simple.
So just to get started, how many people here have heard of quantum computing?
And how many people understand what they've heard? Okay.
There we go.
Checking.
That was good. We didn't even rehearse. We didn't even rehearse that. So you've worked for IBM, you've worked for Apple, you have a quantum computing startup now, but the reason you're here today is because you are the co-author of Quantum Computing for Babies.
Yes.
And we've had this conversation before. You have one of the most clear explanations of quantum computing. Bring us up to date and explain it to this audience.
So greatest thing we ever did was writing a baby's book, amazingly. But a bunch of people have a bunch of different ways to explain quantum computing. And they break those ways in a couple different areas. Sometimes they explain how it works. Sometimes they explain what it is. Sometimes they explain what it's good for. What I think you should do is, the classic coin example. If I have a two-sided coin, I have a heads and a tails, and I lay it on a two-dimensional plane, my palm, the table, whatever, it can be a 1 or it can be a 0, right? And it can never be in anything but those two states. If I take that same coin and I flip it in the air, is it a 1 or a 0 when it's at that apex of that spin? And the answer is it's in a superposition of both 1 and 0. And so if you think of a bit, it is a 0 or 1 state. And if you think of a qubit, it is a block sphere that we can spin in a bunch of different directions, and from that derive a bunch of different probabilities.
So a quantum computer, a lot of people have not seen what a quantum computer looks like, and they don't look like regular computers. Can you explain, and there's a couple different types, how they actually look?
Yeah, I mean, it depends on what you're talking about, right? So what people don't understand is there's 25 different ways to build a quantum computer. And depending on what way you build it, depends on how much you think that is the only way it can be built. So there's ion traps, where you have lasers that are suspending atomic particles. There's cryogenic-based machines, circuit gate machines. There's annealers. The list goes on and on and on. But basically, most of the quantum computers you're familiar with are the ones you see on the web that are cryogenic chambers. So there's these beautiful brass rings in this chandelier, and at the bottom of it is a little chip. And they're in these giant boxes. And the reason there's nothing in the box with that, and you have 8, 10 feet of space around this thing, is to avoid all the environmental interference. Because these things are not computers right now. Now, this is going to be the biggest change in computing since the history of computing, and I'm betting my career that is going to affect everything we're talking about today, from climate change to disease, et cetera, et cetera. It will dramatically affect the human condition. But right now, they're more really good lab equipment for exploring the landscape than they are a computer. And the reason you need all that environmental shielding is it takes a few microseconds, a few seconds for that state to break, and decoherence sets in. There's not really a computer.
So most people think quantum computing is just a much faster computer. That's not exactly the case. So what is the difference? Why is it not just a faster computer?
Well, that's a great question. So it's faster, but not in the way that people often think about it. So don't think of it as a quantum computer as being faster at delivering your content or your cat video on YouTube or whatever. Think of it more along the lines of a computer, let's start with that, can only do things we can do with our hands and toes and counting and sheets of paper. It doesn't matter. It would take us 100 years to solve a problem, and the computer can do it in a fraction of a second, right? So there's problems that are computationally complex, NP, NP plus hard, BQP, et cetera. And these problems take a long time for those computers to figure out. It's not that a classical architecture can't solve the problem. It's that it would take it 100 years, 1,000 years, 1,000,000 years. There are problems that we're looking at right now that would take 4.5, 5 million years for a supercomputer to process. So when we say that it's faster in reducing the evaluation time. That's to say, traveling salesperson is a classic example. We want to send somebody to 14 cities. It's about a 10 to the 11th problem. My computer does about 10 to the 9th on my laptop. 1,600 seconds or so, we can work out all of the possibilities and find the optimized path. If we go from 14 cities to 22 cities, that same computer takes close to 2,000 years. Right? So as we put a number of extra inputs, the evaluation time source, those are also happen to be the problems in chemistry, in drug discovery, in new energy sources and battery technologies. Some of these problems just take forever. So it's not that we have an infrastructure that won't do it. It's that none of us want to wait around 100 years, 1,000 years, 1,000,000 years to find the answer to that problem.
So there's a ton of investment in this category. IBM is in there, Google is in there. There are nation states that are sinking possibly billions of dollars into quantum computing research. Where does StrangeWorks fit into that equation as a small startup based in Austin that you run?
Well, first of all, every nation in the world sees this as a national defense strategy. They see it as part of their plan. China has invested tens of billions of dollars. There's a lot. My shirt is open at the bottom. I'm just going to read that out.
They wouldn't notice, yeah.
Thanks all of you for telling me. No hand signals, nothing.
It's live stream
Great
too.
audience. Best audience ever. Appreciate it, guys. Good to know you have my back. But these countries have invested a ton of money into this because of encryption, because of quantum communications, being able to send messages that no one could intercept, right? There's definitely that investment. Microsoft, IBM, Google, Amazon, everybody, Alibaba, et cetera, they're investing in it as well. Where we fit in is everybody that's investing in it believes that it'll be a vertically integrated solution. That is to say that there will be one quantum computer with one software stack, and that will be the one that you use. And that has never happened in the history of any technology ever. I think it's a ridiculous proposal. I think it prevents the democratization of the technology, and I think it limits access so severely that it's why we don't have better quantum computers now. It's such a small group of people working on them. There are 23 million developers worldwide. There are tens of millions of research scientists, and I want to democratize the access to not just one quantum computer, but to all of them, because as we said earlier, they do different things. An annealer will give you a different answer than a circuit gate will give you a different answer than an ion trap. They don't work in the same way as what we think of when we think of a classical architecture. So I think it's really important to democratize that technology. And I think it's more important to make sure that we start creating a feedback loop where the people who are using the machines are driving the design of the machines.
So you're really focusing on sort of the software side of quantum computing, whereas a lot of the big companies are focusing on the hardware side. Let's build the computer. You want to help train and find that next generation of developers to actually program it and solve problems with it.
Well, sure. I think I disagree with the thought that these are going to be computers in the way that everybody in the field thinks they're going to be. I think of it more like a GPU, TPU, QPU, right? Think of it this way. We used to cross the United States in wagons. And that took 6 months, and somebody died along the way, and maybe you had to eat them. I don't know. It was weird, okay? And then we got the railroad, and 6 months went to a week. But no matter how far we went, eventually you reach an ocean, okay? And then air travel came along, and we're able to travel more extensively around the globe. But air travel didn't get rid of trains, right? There's still trains everywhere. It augmented it. It provided a new capability. Well, these machines, which I believe will end up being co-processors rather than giant machines, I mean, think about it. 10 by 10 box is one quantum computer. It's not like a server rack that you have, right, in your data center. So I think eventually these things will come down to co-processors, and that we'll use them not as the sole source, but to augment classical computing. So for example, what we do in our software is we let you do full program execution. We believe that you're going to write software the same way you do. There's some computational complexity. You'll send that to a quantum computer, get that calculation back or that answer you need, and then you'll continue writing code. That part, though, still requires a quantum workforce, or a workforce that is educated on quantum computing.
And we were talking yesterday that it really is a different type of programming. It's not the same. You're not just going to be a developer that works in a classical model and they'll be able to translate those skills directly into quantum. It takes a different mindset.
Well, this is funny. This is a loaded question because 2 years ago when I started this company, I gave a keynote at South by Southwest, and I was like, developers will own quantum computing, and we talked about this in an interview afterwards. And then a year later, I was like, okay, let's get real. You can't take a developer and turn them into a quantum computing developer overnight. And we don't even know what a quantum computing developer looks like, right? But what we do know is this. Abstraction at this point doesn't help. Meaning that you can't just say, call the teleportation call. Because if everything breaks, and you know it's breaking when you called that, you have to understand something about quantum teleportation to debug it and fix it. It's a very interesting shift, and it is going to be a dynamic, a giant power shift. I mean, the thing I say that upsets all my friends in AI everywhere is like, quantum computing, not AI, is the space race of our day. This, if there was a 1,000,000 qubit quantum computer and I dropped it in the middle of Tokyo or San Francisco or New York or wherever, there would be nobody who even had a remote idea of how to use it, right? I mean, we're missing a big gap there. And it's going to affect things so dramatically. I mean, I cannot emphasize that enough. It's not because I'm in quantum computing. I, 6 years ago, started looking at this area, started studying it on my own, and I was like getting more and more convinced of like, wow, this is not a new processor comes out, or we use GPUs, or now there's TensorFlow. This is a complete shift in the way everything works. It will drive economic changes. It will put enterprises out of business that aren't prepared for it. It's incredible. And when I go to Washington, D.C., when I travel around the world, when I talk to the UN, or I'm at CERN, it's phenomenal that not enough people are paying attention to the change that is happening right in front of their eyes. It's incredible.
One of the big concern with quantum computing, you often hear it's going to be able to break encryption. That you'll be able to break encryption, and it's one of the benchmarks for how strong and how far quantum has come. Breaking encryption would basically destroy the entire internet economy. Is that something we need to be concerned about?
Look, so it will break encryption. Of that, there's no doubt. When? Maybe tomorrow, maybe some tomorrow, 36 months from now. Don't know. But that's not where the danger is. Where the danger is that once you get enough qubits, and there's different formulas, some people think it's 4,096 logical qubits, some people think it's millions, but when you get enough qubits to break, say, an RSA key, the way we've traditionally encrypted documents is we say time and resource. If you have enough time and enough resource, you can break anything, so we make it where it would take you 100,000 years and a bunch of money, and so therefore our stuff is safe. It's kind of a ridiculous way to protect data, right? And so the problem isn't that it's going to do it. The problem is that once it does it, our traditional response would be making the key length longer and making the problem harder. But once we break that, no matter what you do on that key length, it's going to continue to be able to break it with the same efficiency, right? So you're going to be looking in the next 5 years, next 10 years for sure, at completely new models of how we protect data. And there's all types of things that stem off of that. Post-quantum encryption, post-quantum cryptography, right? And those things are being worked on. They're being valuable. So I think we'll have some changes. But then when I go around, I talk to people and I figure out how many people don't know that this is coming. It worries me that we won't be prepared with those new forms of encryption. And that, of course, leads to things like a quantum internet, right? So an internet where there is absolutely no way anybody is going to intercept our data. That sounds great, but there's other physics problems with it. For example, in a quantum internet scenario, there was a paper that said, well, if 3 actors set off a quantum pulse at the right points on a network location, it would destroy the network. When we say destroy the network, we don't mean like your servers got hacked. We mean that the quantum mechanics actually just disappear, like the network doesn't exist anymore technically, right? So there's a bunch of things that we're starting to play with in this realm of quantum mechanics and computing that have never been done before, that are completely fascinating, and it's kind of like science fiction meets science fact, and there's things every month that I'm looking at going like, that's insane.
And you really need to have a physics background to understand the concepts, because when you talk about quantum teleportation, you're literally talking about teleportation. That's not a code. That's not a software or term of art. Like, you're talking about teleportation.
Yeah, I mean, the way I like people to think about it is, in the early days of computers, you had to be an electrical engineer in order to program a computer because you had to understand the flow of electricity between the gates. And by the way, at that point in time, electrical engineers were like, we're obviously the only people that will ever be able to program computers. But enter 13-year-old hacker kid, right? And so in the early days of quantum computing, you really need to know a lot about the physics or be on a team where you have that expertise or whatever to do that. And much like that, I think that by democratizing this software, by getting more people educated on the topic and really pushing this forward, I believe that we'll get not only more advanced technology and get to some solutions that will really help the human condition, but more importantly, we'll have it even. I mean, you can't tell me that there's not some really bright student at some college somewhere in the world that's not an MIT or a Stanford or a UT or A&M or whatever that couldn't use that compute time as effectively or doesn't have a good as idea. I think for us to really see the benefits of quantum computing, we need to get it in as many hands as possible, and that also affects that encryption problem, right? The more people using it, the more people working and thinking about these ideas. I come from an open source background, and so good deal of what we're doing is building community and trying to use the same stuff that happened in open source to democratize technologies, to do that with this technology as well.
So real quick, a couple of weeks ago, Google announced that they had achieved quantum supremacy, that they had solved a problem that would be impossible for conventional classical computing to solve. IBM came out with a release, I think even before they released their paper, saying, no, we can do that. Just give us a couple of days.
Yeah.
Who's right?
It's a weird situation. So
It can be both.
I'm not going to
wade
wade.
At the same time.
I'm not going to wade into that battle. I will tell you this though. Unlike any technology I've been around, there is such a focus on winning a Nobel Prize or changing the world or ruining the financial industry or whatever these goals are, that it was a weird situation. Google's paper got leaked by NASA. Anybody with the internet remembers everything, right? So they were like, well, don't worry, we took it off the internet. And of course, all of us had it and were reading it. IBM hadn't seen Google make an announcement and seemed to lose patience, and they wrote a blog post that says, nope, and also want to use a real computer? Come see us, right? And it came out 2 days, and 2 days later, Google's on the cover of Nature with like greatest quantum breakthrough ever. So it was kind of a catastrophe from that standpoint. And some of the other physicists said, oh, we saw this same thing Google is saying they see in their lab 2 years ago, right? The same phenomenon. But it doesn't matter to me because I was just glad that it took it so much further in the mainstream that people are starting to pay more attention to it. There is no standard for benchmarking a quantum computer. I'm the chair of the IEEE Quantum Computing Standards Group. We've got a team working on that. We'll get it there. We'll probably use tomography or something to measure these machines and see which ones, how you can compare them. So, and saying something supreme, it is a little bit, it's the wrong term of art in my opinion. Because every quantum computer is attached to what? A classical computer that manages all of the functions of it. And they have no memory. So you're taking this data from the classical computer's memory, cooling it down to almost absolute zero, doing the processing, and then warming it back up and putting it on this machine. So I think this whole delineation between this is something that's superior to another one is the wrong way to look at it. I think thinking it's a computer is the wrong way to look at it. It's an amazing coprocessor that will help us solve some of the most urgent problems that we're facing as a society today, and it's super important.
60 seconds left. We've got, what is the most urgent problem that you're looking forward to help solve with quantum computing?
So haven't announced it, one announcement, I keep teasing it, but climate change, right? I totally agree with what David and everybody were saying up here. It's something that has been ignored for a long time, and I think like any complex system, things start building up, and it's, we're seeing the tip of the iceberg now, but we're gonna see the entire iceberg soon. And I think climate science is too easy to disprove. I think that one of the problems we have in having climate deniers is that I can look at almost any study and say, well, there's where there's a thing, and they're over these long period of times. I think if we used quantum sensors, put them out in the world, with some quantum computing, there's a way to build a project and infrastructure in which you could do much closer measurements and be like, look, this happened and here's a change, and that's absolutely undeniable. And this happens and there's a change and there's undeniable. I think that will help sway that, hopefully.
Let's take our score here. How many people feel like they understand quantum computing a little bit better now?
None? Oh, yeah.
I'm gonna call that an improvement. Do you have a surprise at the dinner tonight? Are you going to bring your iPad to the Geek Dinner?
Yeah, so if anybody's interested, so our software, unlike a lot of things in quantum computing, actually works, and you can run on simulators or quantum computers or whatever. And if you come to the quantum dinner, I'll have my iPad. And
it's a quantum dinner now?
Well, okay. I mean, the AI people are there too, apparently. I'm just kidding. I'm kidding. But I'll have my iPad, and we can actually do some quantum computing if you want to really understand how it works.
Excellent. Whirly, everybody.